Okay, this is hour 2 of Physics 1B for October 5th. We're now talking about what's called the kinetic molecular model of an ideal gas. And I grabbed, oh no, let's do that thing again. I grabbed these images and this text from the book so as to make sure that I get all the words right. I'll make this a little bigger. Can you all see that okay? Is that large enough? Okay. I know some of you might be on cell phones, so if you are and you can't see it, I can make it bigger. Okay, so we're going to, again, the goal here is to connect kinetic energy to the macroscopic state variables, which are pressure, volume, and temperature. And in order to do this, we're going to go through what's, I don't know, a pretty long derivation. But we're going to start off with making the following assumptions, okay? So let's look through each of these assumptions so we can understand what they are. So we're going to say that we have a container with a volume V. It contains a very large number, so, you know, on the order of a mole in, of identical molecules, each with mass m. So we're only talking about, like, a vessel that only contains oxygen, or it only contains hydrogen, right? The molecules, we're going to treat them as if they behave as point particles that are small compared to the size of the container and the average distance between the molecules. So the molecules are far apart from each other. They behave as point particles, which means they don't really interact with each other, and the size of the molecules, since they're points, is very small. The molecules are constantly moving. We're going to say that each molecule collides occasionally with the wall of the container, and that these collisions are perfectly elastic. So they're completely elastic collisions with the wall. And we're also assuming that they don't collide with each other. We're also going to assume that the container's walls are rigid and infinitely massive and do not move. They're not really infinitely massive. They're just so big that a gas molecule hitting them isn't going to cause them to move. Okay? Those are our general assumptions. Pretty similar to our assumptions about an ideal gas, and since we're talking about an ideal gas anyway, it should stand to reason that a lot of these assumptions would be similar. Okay? The new assumptions are that when the molecules collide, the collisions are perfectly elastic, and that the container walls can't move. Okay? There's no pistons that can slide or anything like that. All right, so now what we're going to do is we're going to try to connect the molecule bouncing off the wall to the pressure that that molecule exerts when it bounces off the wall. Okay? So for this, we imagine a molecule represented by this dot right here as it elastically collides off of a wall. There's an arbitrary x and y axis in this picture. The molecule has a velocity that's kind of at an angle like this before the collision. It has an x momentum that's negative vx. It collides with the wall. It bounces off. After the collision, its velocity in the x direction is going to be the same as it was before, except for now it's going to be pointing to the right. So it was going left, now it's going right, and the vy's are going to remain unchanged. So the velocity component parallel to the wall doesn't change. The velocity component perpendicular to the wall just simply reverses direction. It's the same magnitude before and after the collision because it's an elastic collision, right? What does elastic collision mean? How is it different from an inelastic collision? I said elastic and I didn't even think to remind. What's the difference? No energy is lost, right? So in order for kinetic energy not to be lost, the velocity of the particle before and after the collision has to be the same. It is okay if it changes directions, however, as long as the value of the x component doesn't change within the collision, right? Okay. So that's what we see is happening, and then I wrote down here that the change in momentum is going to be 2 times m times vx, right? And so I'm going to write that up here, that the change in the momentum of our particle And I guess I actually have to use what the book does, which they use capital P for momentum. So the change in momentum in the x direction should be equal to the momentum after the collision, which is this. So mass times Vx, the absolute value of this, or the magnitude of this. We have to subtract from that the momentum before the collision in the x direction, which is negative mvx. And so that's how you get the change in momentum in this case is going to be 2 times m times vx. Because the negative. It bounces off the wall, and that's the change in momentum of the particle. Okay. Now we're looking at this picture here. Okay, so this is an individual molecule, and now what we want to think about is what happens for all of the molecules, basically. So this picture right here says, suppose I have a wall and I create an arbitrarily sized cylinder, and I say that for a molecule to strike the wall in an area A during a time interval dt, the molecule must be headed to the wall, and it has to be within the shaded cylinder of length Vx times dt at the beginning of the interval. So imagine a wall on the far edge of this cylinder right here, and suppose that it's moving to the left. It should be able to make it to the wall in some time interval that we call dt, where the size of the cylinder is given by that distance, right? That's how far the molecule could move in some time dt would be the velocity times the time interval that we're talking about, right? And there, in principle, are multiple molecules within this region here. And as long as they are within the region and moving to the left, they should hit the wall, right? We're going to make the assumption that half of the molecules within the cylinder are moving to the left and half the molecules are moving to the right. So half of the molecules are moving to the left, right? And we can say then that the number of collisions that occur with the wall, so the number of collisions is going to be related to the number of particles per unit volume that are moving left. So this is going to be equal to the number of particles that go left of the gas per unit volume multiplied by the volume of the cylinder. And we're going to say half are moving left. All right? So that means that the number of collisions that we're going to see is going to be equal to half of the particles move left. The number of particles per unit volume we're going to call big N divided by the volume V. And then we're going to say that the volume of this container right here is going to be equal to the area of the wall, the cross-section of the wall, multiplied by Vx times dt, because area times the length of the cylinder is going to give us the total volume of the container there. Right? So N over V is a macroscopic representation. This is the volume of just a small cylinder. So this would be, in the denominator here, is the volume of the container of, we'd say all, I don't know how to say it, it's just the volume of the container. And this is the volume of the cylinder, because we're just looking at a little piece. N over V is the total number of molecules divided by the volume. And that tells us the density, effectively, right? The number of molecules per unit volume. And we assume that that density is roughly uniform over the whole system that we're talking about. The whole system is going to be some larger volume, V, that will contain a total number of molecules N. And we say half of the molecules that are in this region are going to move to the left, and that's going to be where the collisions are going to occur. Okay, I'm going to stop right there before we go into more mathematics, because that's the first equation. Does anyone have any questions? I suppose I should say something about like just what we're talking about here. The idea is you have some volume, right? It's closed off. Contained within here are N gas molecules. And the total volume is V. And if we take the number of gas molecules per unit volume and we multiply by the volume of this smaller cylinder right here, we figure out how many there are inside there. And we say half of them are going to collide with the left wall here. So N is the total number of gas molecules in the system. Does that make sense, Ruja? Just you've got all these molecules in here. Bunch of little tiny molecules. Some of them are moving off this way, some are moving off this way. Some of them will hit our little section of the wall here that we're calling A, and we're just looking at ultimately what kind of force they place. Okay, so we're going to combine these two together here and say that the change in momentum, the total momentum change we're going to get. So if an individual molecule delivers this amount of momentum, or has this amount of change in momentum right here, 2mvx, that's one molecule. M is the mass of a single molecule. Vx is the velocity of a single molecule. If I take this quantity and I multiply by the number of collisions, I'm going to get what I would call the total momentum change. So the total change in momentum within this little cylinder right here is going to be equal to, we'll call this change in momentum, is going to be equal to the quantity that we just described, the number of collisions, multiplied by, this is all of this. So that's the total number of collisions with the left wall. And we need to multiply this by the momentum change for each collision, which is 2 times m times vx. And I really should be putting like absolute value signs in here, but it's hopefully it's okay if I write like this. So that's the total change of momentum. We take the total number of collisions that we have right here, and we multiply by the momentum per collision, basically. And we get that expression. This can be simplified a little bit because the 2's cancel. There's Vx here as well as here. So you end up getting N times A times dt divided by the volume and then multiplied by m times Vx. But Vx is squared now. Now this is the total change in momentum of all the particles that undergo this bouncing process, right? They go in here, they bounce off. Go in here, they bounce off. They go in here, they bounce off. A whole bunch of particles do that, and when we sum up all of the change in momentums, this is what we get, okay? So the next thing that we'll do then is we're going to divide the dt to the left-hand side over here, And we'll get that the change in momentum per unit time is equal to n times a divided by v times m times vx squared. And then we say, well, what is this thing right here? This is the rate of change of momentum with respect to time. What does that represent? If I take the derivative of the momentum with respect to time. It's force. It's not acceleration, but it is force. So Newton's second law, it's related to acceleration. This would be, well, I'll write it down. So Newton's second law, there's two ways you can write it. You can either write it as force is equal to mass times acceleration, or the force could also be related to the derivative of momentum. So this would technically give us, specifically, the x component of the force in this case. Okay? The x component of the force. And it's related to acceleration, right? But it would just be, you'd have to divide by the mass to get the acceleration in this case. Which we could do. All right, so we get that. So we now know the force, right? But our goal in this case is to relate this value, the x velocities of the molecules, to our more general macroscopic measurements of gases, which are things like pressure, volume, temperature, right? So how could I get pressure out of this equation then? Not momentum, but pressure. Is there anything I can rearrange over here so I can turn this into telling me something about pressure? Yeah, force divided by area, exactly. The area is already right there, so if I take the force and I divide by the area, that's going to give me the pressure P, right? We've already got area right here, so we divide the area over here and we're left with just N over the volume and then mvx squared. Okay, so we're going to keep going with this, but I'm going to kind of go back and address some of the... So this is a nice equation though, right? Pressure is equal to the number of molecules per unit volume, which is basically the density, multiplied by this quantity, m times vx squared. And this probably looks like something you've seen before, right? mv squared. Now, in this model, I don't think I explicitly mentioned this, but we're assuming that all the molecules have the same Vx. That is not a reasonable assumption. The molecules are going to have random velocities. We know that if we were to sum over all their velocities, the average x velocity would be 0, because half would be going left and half would be going right. But individually, they do not all have the same velocity, okay? That assumption is just, it's not realistic, okay? So we need to somehow deal with the fact that these velocities are not actually the same, okay? So what could we do? Well, we know that for an individual interaction, for the individual case, that this equation right here tells us the momentum change for one molecule, right? And what we could do, really this one, I guess. This tells you the momentum change for a single molecule. What we could do is we could say, well, there's some molecules that have higher velocities and lower velocities, so we could kind of figure out what those velocities are by some method, and then we could go through and we could kind of sum up all of their possible interactions with the wall. And to do this, we'd probably have to assume some normal distribution of velocities maybe, or something like this, where, we assume that some of them are moving really fast, some are moving really slow, but most of them are moving on average about the same. And then we would just sum up all of those individual momentum transfers, right? And that would give us an idea of what the total force, and that's what this represents right here, would be the total force, if we just summed up all the possible different ones. But effectively, at the end of the day, that involves kind of just averaging over all of those different velocities. This sounds very, very familiar, almost like Chem B. Did you talk about this in Chem B? I wouldn't be surprised. I wouldn't be surprised. So maybe we'll see when the equations we get to at the end. You got to tell me if they're similar to what you learned in chemistry, because I think they probably will be. You talked about molecular velocity for sure. Yeah. So total force we could get if we knew something about the averages, right? So let's talk about what would happen if we start to use averages. So we've got this relationship. We'll hold this in our back pocket, and we'll come back to it. Okay. So what if we were to use average velocities instead of using this incorrect assumption that all the molecules are assumed to have the same magnitude? All right. So if we average over all the x velocities, we can learn something about this. In general, a particle that's moving in a three-dimensional space is going to have three components for its velocity. It's going to have a vx, it's going to have a vy, and it's going to have a vz. Each individual particle, because it's moving in a three-dimensional box, is going to have three components for velocity. And I can find the total velocity of the object squared by effectively using kind of the Pythagorean theorem. That would represent for a single molecule with velocity v, its velocity is related to its components via this equation right here. Likewise, whatever the average velocity squared of my molecules is, that's also going to be related to the individual x, y, and z average velocities. Oops, squared goes inside of here. So we take Vx squared, average, whoops. We take the average x velocity squared. We take the average of all the y velocities squared. We have to do squares too, because otherwise it would just be 0. If you average over just Vx, you get 0. You average over Vy, you get 0. But if you average over Vy squared, you don't get 0. Let's see, Vx, Vy, and then Vz squared average. However, no matter how we set up our coordinate system, there's no reason to believe that x, y, and z are going to be unique. We could set up a different coordinate system where we rotate it a little bit and redefine what we mean by x, y, and z. There's no gravity that's going to be important. So the y velocities, whereas if we're talking about the y velocity of a baseball that you throw through the air, the y velocity is going to be heavily affected by gravity, right? The acceleration due to gravity is going to change the y velocity. It won't change, for example, the x and z velocities, right? But we're not going to worry about gravity. So gravity doesn't matter. These molecules have extremely small masses, so they're largely unaffected by gravity, at least within the region of space that we're describing right here. Gravity does pull on them. It just isn't going to have nearly as much of an effect because they're going to be moving very quickly, as we'll see. So gravity doesn't matter. There is no preference between x, y, and z, which means it should be the case that when we average over the x velocities squared, that there's no reason why this should be any different than averaging over the y velocities squared or averaging over the z velocities squared. All of these should be equal to each other. And what that means is that our equation right here, we can relate it, but so if they're all equal to each other, right? Then the other way we can write it is to say that v squared average is just equal to 3 times Vx squared average, which means that Vx squared, we average over all of those, is just equal to v squared average divided by 3. And we can plug this one in there. There's no difference between x, y, and z, and we can use this relationship right here. Okay, I'm a little bit, oops. Need to leave a little bit more room here. Not much more, we're almost there. Just to be safe, we'll leave a lot of room. Okay, so knowing that, we plug it back into this equation right here. Let's use a different color for this next section. So the pressure P is now going to be equal to the number of molecules divided by the volume of the container multiplied by the mass of this is a mass of a single molecule, and now Vx average is going to be just v squared average. We take the average velocity squared of all the molecules, and then we have to divide by 3. All right. Rearranging this a little bit, what we can do is we can multiply the volume to the left-hand side, and we get that pressure times volume is equal to the total number of molecules divided by 3, multiplied by m times v squared average. And now what we want to do is we want to take this mv squared thing and we want to turn it into something that we know, okay? For an individual molecule, for one molecule, 1/2 multiplied by the mass of the molecule multiplied by v squared average, this represents effectively the average kinetic energy per molecule. Does that make sense? This is the average kinetic energy per molecule. You could say it's the kinetic energy of a single molecule effectively, but it's the average, right? Because some of them are going to be fast, some are going to be slow, but this gives us the average kinetic energy per molecule right here. So if we want to put that into here, what we need to do is we need to throw the 1/2 in, but we can't just arbitrarily throw 1/2 in. So what we'll do is we'll multiply by 2, and then we'll divide by 1/2. So that doesn't change anything. We just need to get the 1/2 mv squared part in here. Okay, so we're getting pretty close here. We have pressure and volume, and they're related to... Oh, I should have mentioned one other thing here. This isn't just average kinetic energy. It's the average, we'll input it in here, translational kinetic energy. Oops, misspelled that. It's the average translational. Because the molecules, they may be doing other things too. We're going to find they could roll or they could bounce. So there we go. And what we can do then is we can say that if this is the average kinetic energy per molecule, if I take n and I multiply that by 1/2 m times v squared average, what would that represent then? If I take the total number of molecules and I multiply by the average kinetic energy per molecule, what is this going to represent? Or the total. It's the total kinetic energy, right? So because we're multiplying by, so you take, this is like the average kinetic energy per molecule. You multiply by number of molecules. Yeah, I can see how you'd say it's the average kinetic, but see, now it's just the total energy, basically. This is the total kinetic energy. We're going to label this as K with a little tr, and we're going to say this is the total kinetic energy of all the molecules of the system. At least of the gas molecules, okay? So then this equation becomes a little bit simpler. So now what it's going to say is basically just if I take pressure and I multiply by volume, that happens to be equal to 2/3 of the translational kinetic energy of the system. But we also know, since we're talking about an ideal gas, what is P times V equal to? What's the pressure of the gas times the volume of the gas equal to? nRT, yep. So this is also equal to N times R times T. I think we're actually getting to the point where we actually have some of these things here. There we go. We've got this one now. So what does this equation say? Make this a little bit bigger. The average translational kinetic energy of an ideal gas. So they still use the word average. Maybe I was wrong. That's what you guys said too, right? Maybe I said it wrong. Let's think about this. A single molecule has this energy, right? That's the energy, the average kinetic energy per molecule is this. You multiply by N, and now you get the average translational kinetic energy. It's the whole gas, though, right? I'm really confused by this word average now. It feels like it should just say translational kinetic energy of an ideal gas. What am I thinking that's wrong? Okay, Kenny writes it's the average kinetic energy of the whole. And then Miara's, you're saying the total divided by N would be the average. So average N means total. Okay, so it does mean the total energy then, is what you're thinking, Miara's. Is that right? Yeah, okay, we agree then. That's good. That's just I'd be kind of nitpicky. That just bothers me a little bit. Okay, so I mean, you see that it's related to state variables, right? It's related to temperature. It's related to the number of moles of the gas. It's really, if you think about it, it's really just related to temperature, right? It should be obvious that if you have more gas inside of there, you're going to get more energy at the same temperature. So I feel like that goes without saying. So it's really just it's just 3/2 times the temperature at the end of the day. That's pretty remarkable if you think about it. That the energy, the translational kinetic energy, you can either think of it as being 3/2 times pressure times volume, or you can think of it as being 3/2 number of moles times R times T. That's pretty amazing. This is a direct connection between temperature and kinetic energy, and it tells us that temperature is a measurement of kinetic energy. That's what it's measuring. When we measure the temperature of a gas, the temperature of a solid, the temperature of a liquid, what we're measuring is how fast, on average, the molecules are moving. And that's truly amazing, I think, is that there's this direct connection between this thing we call temperature, hotness and coldness, and how fast the molecules themselves are moving. So on a cold winter's day, when the temperature is really low, the molecules aren't moving very quickly, and they're not able to transfer energy to your skin because they're moving a lot slower. They carry much less energy with them. But then on a hot summer day, the molecules in the air are moving much more quickly on average, and what that means is that they can very quickly transfer energy to your skin, and they can warm you up. You got more molecules moving more quickly. That means, if you think about it, more molecules moving more quickly means that's more collisions that are occurring, right? And at the end of the day, what we learned here is we learned a few things. We learned that pressure of a gas is related to the energy of the gas as well, right? So pressure comes from individual collisions with the gas wall. If you think about a balloon, for example, inside of a balloon, what you've got is you've got all these little tiny molecules in here, all these little gas molecules, and they're constantly zipping around and colliding with the balloon walls. And that process of all these collisions occurring with the wall are what give the impression that the surface of the balloon is this nice smooth shape. But in reality, at the point where the container walls are, you have all of these tiny little collisions that are constantly hitting the side of the balloon. And when you average over all of those collisions, you get this nice smooth surface of the balloon. And when we talk about how tight the balloon is, or like when you try to squeeze it, you're talking about pressure, and that pressure is quite literally created by individual molecules colliding with the system. So this helps to connect the idea of temperature, the idea of pressure, directly back to physics 1A, you might say, to Newton's second law, because that's ultimately what we used here. We used Newton's second law, we used the concept of what kinetic energy is, and it connects temperature. And I think that's truly amazing, that temperature is nothing more than just kinetic energy at the end of the day. It's pretty cool, I think. Do you guys have any questions or comments or thoughts? Or you saw this equation in the meme of cooking a chicken by slapping it. There you go. How many slaps does it take to cook a chicken? And how hard do you have to slap it? Would it work? Hard to slap to get a steak rare. It's probably a little safer to be slapping steaks than slapping chickens, because steak you don't have to completely cook it all the way through for it to be safe to eat, whereas chicken, it's a little bit sketchy if you try to eat it, even if it's a little bit rare. Okay. So, and of course you guys are joking, but I mean, the idea you're describing is not necessarily wrong in the sense that, you know, these molecules, as they're moving, they're basically slapping against the side of the wall, and that's what creates pressure, and it's related to their temperature too. So I kind of definitely get where you're coming from there. Okay. So what do we do next? So next, what we can do is we can write this equation in different ways in order to kind of find different kind of pieces of information. One thing we can do is we can look at, I should kind of box in some of these equations here. We can look at this equation right here. Come on. Shape box. This equation here. We can look at that one. And we can say that if we take the translational kinetic energy and we divide by the total number of molecules, that gets us back to 1/2 mv squared average. This gets us back to just the energy for a single molecule. The average translational kinetic energy of one molecule is equal to this. So according to the equation that's from the book right here, if we take 3/2, if we take 3/2 and then we divide by n, so we're going to have little n divided by big N right here. So the number of moles divided by the number of molecules. Easy to get these confused, but little n is the number of moles and big N is the number of molecules, the total number. We get that expression, but the number of moles and the number of molecules are related to each other, right? How are those related to each other? What's the number that relates the number of moles to the number of molecules? Avogadro's number, that's right. So Avogadro's number tells us that if you know something about moles, that 6.022 times 10 to the 23 atoms or molecules per mole. So if I've got n over n, so if I were to write this like this, big N, the total number of molecules, divided by the total number of moles, should always be equal to Avogadro's number, right? And since we have little n over n upside down, the Avogadro's number is going to appear in the denominator. So now our equation is going to become 1/2 mass times V average, V squared average. This is going to be equal to 3 times R times T divided by Avogadro's number. And it turns out that if we take the gas constant and we divide by Avogadro's number, this is, oh, I left out a 2, didn't I? I'm sorry about that. There's a 2 down here too from that one. So if you take R, the gas constant, and you divide by Avogadro's number, okay, this would be equal to, so let's think about what these are. R is 8.31, and it's joules per mole Kelvin. And if we divide that by Avogadro's number, which is right here, which is atoms per mole, I'm not going to rewrite it because you can just see it right there. What we're left with is a new constant that has units. That's right, joules. The units for this constant are going to be joules per atom per Kelvin. And the value of it, you can do it yourself. Take 8.31 and divide by this number right here. What you're going to get is, you can verify if I wrote this down right or not, 1.38 times 10 to the negative 23. 10 to the negative 23. And this is called KB. Okay, this is called Boltzmann's constant. Oops. I think it has two ends. This is a constant that you'll see show up quite a bit in chemistry, physics. It'll show up in physics 1D as well. It'll show up a lot in this class, the Boltzmann constant. You can see that it's directly related to two other constants that you've already known about. So it's not exactly like something new because it comes from R over NA, but nonetheless it is a constant we use quite a bit. And given that definition, right, that R over NA is equal to K, this equation becomes 1/2 m v squared average is equal to 3/2 Boltzmann constant times temperature. That is another one of our equations. If you take 3/2 the Boltzmann constant times the temperature, this gives you the average kinetic energy per molecule. Now that is a really simple equation, right? It's literally just a constant times temperature, which this tells you that since the Boltzmann constant is just, it's a representation of the joules per atom per unit Kelvin, this is really just a conversion factor. If you think about it, it's really just a conversion factor. And this is a direct connection between just kinetic energy and temperature alone. And this is too. I mean, don't get me wrong, this says the same thing. This just says for the entire gas, this says per molecule, but this is the one I always remember. It's just the energy of a single molecule is 3/2 kb times T, on average, basically. Okay. I assume that's probably one of the equations I have right here. Yep. Just put that one right there. So you've got something to keep in mind here is you have to remember that this is the mass of a single molecule right here. It's a single molecule. So that's something you have to calculate. We'll do that in some of the problems we'll do. You've got Boltzmann constant. They just use K. I put KB because there's a lot of other Ks in physics. And then you've got the temperature, the average value of the square of the molecular speeds, and then here's the value of the Boltzmann constant that we got right there. Okay. Any questions? All right. So a couple other things that we can say. We can kind of play this game where we write these things in a little bit different ways here. So if we take if we talk about molar masses, so molar mass, capital M, is equal to what? Avogadro's number, which is the number of atoms per mole. If we multiply that by the mass of a single molecule, we get what's called the molar mass. And the molar mass, this is the thing that you get from the periodic table. Right? The molar mass of carbon is like 12, for example. 12, and that's in grams per mole. So given that, what we can do is we can multiply Looking at my notes here, I'm getting confused by what I wrote. Oh, so yeah, right here, this equation. Actually, it's probably the easiest to start from the equation above it. So this equation here, it has the Na already in it, right? And we need Na times m to show up, right? So we want to multiply Na to the left-hand side. So we'll have 1/2 Na multiplied by the mass of a single molecule. That's going to be our molar mass. That's multiplied by v squared average. And that ends up being equal to 3/2 just R times T. Okay, so that gives us a new equation, which says if we take 1/2 the molar mass times the velocity squared average, that this is going to be equal to 3/2 RT. This is going to represent average kinetic energy per mole. Right? Because this would be, the molar mass is, the units for molar mass are grams per mole. So if I take that and I multiply by this, I get basically the kinetic energy per mole, right? Kinetic energy per mole is going to be 3/2 RT. One other thing we can get from this is if we look at our, because now we have this symbol K, if we take PV equal to nRT, there's another version of this that's exactly equivalent, which is just if I take pressure times volume, it's going to be equal to, in a similar way, big N times K times T. So Boltzmann constant times the total number of molecules times temperature, okay? You can prove for yourself that little n times r is equivalent to total number of, so n is number of moles, big N is number of atoms. You can prove for yourself that little n times r is equal to big N times kb, just by using the definition that r over Na is equal to the Boltzmann constant, right? So you can replace r with Na times Boltzmann, but then you get little n times Na, so you basically use these two equations. You can prove that this is true. So that's a nice relationship that we can use. And then finally, what we can say is, I feel like we're doing so much stuff all at once. I kind of want to take a break, but this is the very last step. We can actually talk about, kind of on average, what the velocities of the molecules are, because this tells us the average velocity squared and how it's related to temperature. So we can't know exactly what the velocity itself is. Oh, I don't have to derive this because it's all written here, I guess. We'll just use this. So in general, what we can say is that we can talk about what's called the root mean square speed, or RMS speed, VRMS for short. To get the root mean speed, root mean square speed of a gas molecule, all we have to do is to take the square root of the squared average velocities, okay? And from our equations that we have written up here, if we use this one for example, here, let's put it down here so we can see it like side by side. If you're to solve this equation for v squared average, you know, the halves will cancel out. You'll have 3 kT. You have to divide the mass, and then you need to take the square root. So what this tells us is if I know what the temperature of the gas is, I know the Boltzmann constant, and I know the mass of a single molecule of the gas, that if I take 3 kT over m and take the square root, that's going to give me what's called the root mean square. The root mean square. And this is, you know, it's not like the mean. It's like this. It's you take the average squared velocity and then you square root it. So why do you do this? What's the point of doing this? Well, if we were to average over just the velocities themselves, I average over all the velocities of the molecules, right? We're going to get 0 because there's going to be just as many moving left as there are moving right. So this is a much more representative sample of like how fast the molecules are moving, okay? Because we don't care about positive velocities, negative velocities. We just care about how fast is it going, basically. Just how fast it's going. And if you square something and you take the square root, you're guaranteed to get a positive number here. We're just taking the positive root. This equation, we can also play the same game, but instead of using the mass of a molecule, sometimes it makes a lot more sense to use the molar mass. So this equation right here, we can solve to get this one right here. So it's important to understand when you're using these equations, the biggest thing that I see people make mistakes with these in the times that I've taught this course previously is just forgetting that little m represents the mass of a single molecule. It's not the mass of the gas itself, because maybe you have problems where it'll say like you have a container that contains 20 grams of oxygen or something like that, and people will commonly put the 20 grams down here. It's not that. It's the mass of a single molecule that shows up in this equation to find VRMS. So that's why I think the one on the right is a little easier to use, because you can go look molar mass up in a table, You can just go look it up in a table. Just for example, nitrogen, N2, has a molar mass that is about 28 grams per mole. Oxygen, the molar mass of oxygen is about 32 grams per mole. Oh, and by the way, you actually have to convert these to kilograms to use this equation, right? This needs to be in kilograms per mole. All right. But something like hydrogen is a very light gas, right? So hydrogen gas, the molar mass of hydrogen, I think, is 2 grams per mole. Oops, right here. 2 grams per mole. So if you think about what effect this is going to have here, if you think about what this tells us. So we started off with pressure, we talked about force, and now we're just talking about speed. The speed of the molecules, the root mean square speed, is directly related to the temperature. It's also related to the molar mass, though, right? So if I think about in our atmosphere where we have some oxygen, we have some nitrogen, we have some carbon dioxide, and think about the comparison between if we also had hydrogen in our atmosphere, which one would be moving the fastest? Would it be the oxygen, the nitrogen, or the hydrogen? Which one would be moving the fastest? Hydrogen. And it would be significantly faster, right? I mean, we're taking square root, right? Let's look at this as being like 16. Then in the denominator here, you're going to be dividing by 4 times root 2. Whereas here, you're just dividing by basically square root 2. So the molecules of hydrogen are going to be moving quite a bit faster. And this actually has an effect that we can describe in the following way. On the Earth, you can calculate something called the escape velocity of Earth. The escape velocity. The escape velocity for Earth is about 11 kilometers per second. And this is something that if you want to verify it for yourself, I believe you can get it by doing this calculation. I would need to go and go back and look just to make sure, but I'm pretty sure that the escape velocity of Earth is related to 2 times the gravitational constant times the mass of the Earth times the radius of the Earth, and you square root it. That gives you the escape velocity, basically. It's about 11 kilometers per second. If we chose to calculate what VRMS is, let's just do a quick calculation of what VRMS would be for a hydrogen molecule, okay? What's that going to be? So we would take 3, we're going to use this one, 3 times R, which is 8.31 joules per mole Kelvin. And we multiply by temperature. Now let's choose to use the temperature of our atmosphere. Let's look at the speed of H2 molecules at about the temperature of the surface of the Earth, so about 70 degrees Celsius, which is what? 343 Kelvin? Is that right? That's right. So let's use the speed of H2 molecules at this temperature. So we multiply by 343. And like I said, you need to divide by molar mass, but it needs to be in kilograms per mole. So if the molar mass is 2 grams per mole, that would be 0.002 kilograms per mole. Right? What is that number? Okay, I got a new phone. This is taking me like a second to get my... Okay, there we go. So it's 3 times 8.31 Can anyone tell me what they get if they do this calculation? What do you get? Anyone want to answer that? Pretty simple. Just multiply these numbers. Take square root. Okay, so about 2 kilometers per second. Right. Okay. What do we know about hydrogen in our atmosphere? So 2,000 meters per second, so about 2 kilometers per second, right? What do you guys know about hydrogen in our atmosphere? Is there any? There's not a lot of it. There's very, very little. That's right. What about hydrogen on the surface of the moon or on the surface of Mars? Helium too, right? Very little helium in our atmosphere. There's helium trapped in like rocks underground, right? But we don't have a lot in the atmosphere, right? Same thing goes with hydrogen as well, right? What about the surface of the moon? Is there very much hydrogen on the surface of the moon? What about oxygen? What about carbon dioxide? There's like nothing, right? There's some, but there's not a lot, right? Not much of an atmosphere at all on the moon, right? Why do you think that is? Now, if I tell you the escape velocity for our planet is 11 kilometers per second, this would mean if I got a rocket moving this fast, it would be able to escape the planet, right? And if I was to write down what the escape velocity for the moon is, it's much, much smaller. So you can imagine that... Go ahead. It's not any easier for molecules to escape the atmosphere than it is for a rocket to escape the atmosphere, as long as you neglect like the drag forces. Rockets are technically a lot harder to push out because they have to deal with drag forces. The mass of the particle doesn't show up in this equation, so it doesn't actually matter. The thing is that when I say... Yeah, that's right. But what about planets that are bigger than Earth? Are there any planets that do have a lot of hydrogen gas on them? The gas giants, exactly. They're called gas giants because they have a lot of gas. I think the escape velocity on Jupiter is like 60 kilometers per second. Now, this is the thing where I want to emphasize this. So we know that there's not much hydrogen in the atmosphere, and this is supposed to be an explanation as to why. But if you just think about it in terms of the velocity number, 2 kilometers per second is about a fifth of the escape velocity, right? But the thing is, this is the root mean square speed. Some of the particles are faster than this. Some of the particles are slower than this. And if we look up like let's see, gas velocity. I didn't see a picture for this in your book, and I don't know why, but this is an example of kind of what those things look like here. They call this the Maxwell Boltzmann distribution. You can see a lot of the same calculations we're doing right here. And where is it? Right here. There we go. So this is RMS velocity in meters per second. The RMS velocity, I believe, is the peak of these curves right here. Okay, and this is for different temperatures, basically, right? This is the fraction of molecules within 10 meters per second of the indicated speed. Okay, and with hydrogen, if you look at this, they're going really fast, basically. And I don't know what temperature this is, but my point is that there is a distribution, and it flattens out like this, where you have a whole lot of the molecules are moving really fast. And how fast the molecules move is not constant, because they're going to interact with their environment, they're going to interact with all kinds of things. So what it means is that like there's a lot of molecules that are moving way faster than this. And if they move close to Earth's escape velocity, they're going to escape from the planet. And that's why you don't see much hydrogen on Earth, but you can see these type of things, oxygen, nitrogen, because they're heavier, and because they're heavier, they have a lower RMS value, which means they can get trapped on the planet. But if you have a low escape velocity like on the moon, you're not going to have as much of an atmosphere if you have, so. Anyway, that's a connection between, like, the composition of your atmosphere depends on how much gravity there is and how hot it is too, right? If the temperature's really hot, the RMS speeds are also going to be higher, right? And maybe if it gets too hot, all the stuff you want to have in your atmosphere, like oxygen and carbon dioxide, may not be able to stay there. Okay, so I went a little longer than I wanted to there. We'll take a break and we'll come back. But anyone have any questions? We're going to do some problems when we come back.